Now in this class, let us discuss about Zener diode in the diode circuits topic. So Zener diode is same as the PN junction diode, but the difference is Zener diode is highly doped than the normal PN junction diode. Normal PN junction diode we use only in the forward bias region. In the reverse bias region, it will be open circuited. That's what we discuss in the normal PN junction diodes. But when it comes to Zener diodes, in the reverse bias also we can use the Zener diode as a voltage regulator. So normally when you consider the forward bias region, so now for the same PN junction diode, after crossing the cut-in voltage, the current will increase rapidly. So here we use only in the forward bias region as a conducting element for the normal PN junction diodes. In the reverse bias case also, normally when you use the PN junction diodes, in the reverse bias region, after some threshold value, the diode will conduct heavy currents, but that will destroy the diode. But in the Zener diode case, we dope the Zener diode with excess electrons, with excess holes as well as electrons. So highly doped PN materials we use. So here in the reverse bias case, after crossing the Zener voltage, the current will be very high, but we will keep a maximum limit. The current I maximum will be there. So for this, up to this I maximum, we can use the diode. We can use the diode in the reverse bias region. So here, even though you are increasing the voltage, the current will increase, but voltage across the Zener diode will be same. For even though you are increasing the current, so the voltage across the Zener diode will be same every time. That is VZ, that is Zener voltage we call as. So the symbol for Zener diode is, this is the symbol we use. So normally normal junction diode, but here we just like use a Z. So this is the symbol for Zener diode, and the I/O characteristics of Zener diode is, in the forward bias region it is same as the PN junction diode. In the reverse bias region, after crossing the Zener voltage, it will have same voltage across the Zener, but current will increase rapidly. We use up to the maximum limit here. And when you see the equivalent model for Zener diode, in the forward bias region, so in the forward bias region means, observe this is Zener diode circuit. So this is Zener diode, positive side is connected to the positive terminal of voltage, and here negative side is connected to the negative side of voltage. So here the electrons, here positive side the holes will repel, here negative side electrons will repel. So this junction will go into forward bias region. So when it goes to forward bias region, the voltage across the forward bias region will be 0.7. So that voltage source will be there. So the voltage across the Zener diode will be only 0.7 in the forward bias equivalent. So normally when you case ideal cases, we can take it as 0 only. In the ideal, this is practical one. This is practical. But when you take ideal case, in the ideal case we will take it as just completely 0 voltage. Because in the ideal we consider the across forward bias will have 0. But when it comes to reverse bias, in the reverse bias region, observe this is PN junction diode. So here positive side we are connecting negative, here negative side we are connecting positive terminal of the voltage. So here the diode will be in the reverse bias, but here the condition should be, so whatever the value of V you are applying, this V should be more than VZ. That means here if you apply more than the Zener voltage, when you apply more than Zener voltage, then only diode will go into reverse bias region. Otherwise diode will be in the open circuit mode. That means observe, when you are applying less than VZ, here current is very less. Normally in the forward bias region we consider currents in milliamperes, but in reverse bias region we consider these currents as in microamperes. So they are very negligible. So from 0 to VZ, in this region the Zener diode you can consider as open circuit. But after crossing VZ, the output will be only at VZ only. So here after when V is more than VZ, then this diode will be in the reverse bias region. So when it is in reverse bias region, we will take the equivalent like this. And here observe the polarities. So actually this is anode side, this is cathode side. We are taking plus and minus like this. But here this is anode side. So anode side you are taking negative here, and cathode side you are taking positive. So here the polarity is different here. So this VZ polarity is different. So here this is in the reverse bias equivalent of Zener diode. Mainly this model we use in the voltage regulators. We will discuss in the next topic.